Yes. Our second speaker for this afternoon is Professor Martin Rubey from the University of Vienna. There is his title, Promotion of Kreweras.
So thank you very much. So this is joint work with Sam Hopkins, and obviously the picture on the right hand side is missing. So could you make the clicker work for me? So I'd like to start with a problem you may have seen before. So how many ways are there for 2n people to cast votes? So we have an election for 2 candidates, Alice and Bob, such that Alice and Bob both receive the same amount of votes. So both receive n votes, and Alice never trails Bob. And the first few voting configurations are here. Very likely you have seen them before. You may know them as big words, but you may also know that they can be seen as linear extensions of this poset. And you might also know that there's a very nice formula enumerating these. And one thing I like about these words is that there is an action on them. So we like dynamics. The promotion of a Dick word, W, is defined as follows. You chop off the first letter. And then what remains is not a Dick word anymore, because now we have more B's than A's. We're going to fix this. So just imagine the first letter A is gone. And then we look for the first violation of our rule. So we have A, B, that's okay. A, B, A, that's also okay. A, B, A, B, that's okay. A, B, A, B, B, that's not okay, because Bob has 1 vote too many. So what we do is we replace this B with an A and sort of move it to the end. And what you get is a Dick word, again, a voting configuration. So that's promotion on Dick words. Yeah. And one reason I like actions is that they have characters. So what's the character of a cyclic action? If the cyclic action has order n, that means you have to apply it n times to get the identity. Then for our purposes, the character is the polynomial of degree less than n, defined as follows. If I plug in an kth power of a primitive nth root of unity, the polynomial should evaluate to the number of fixed points of promotion to the power of k. So that's the one definition of character that will work for us today. And then there is a very nice observation by Dennis White in 2007. First thing is promotion on Dick words has order 2n. And second thing is we can compute its character. It's the most naive Q analog of the Catalan numbers. You just replace round brackets by square brackets, and it's not even very important what it is. Okay. Now that's all. Oh yeah, and one very nice way to visualize this is as follows. There's a very natural bijection between Dick words and perfect matchings. And I draw the perfect matchings, non-crossing perfect matchings, excuse me, in a peculiar way on a circle. And this bijection has the following property. It intertwines promotion and rotation. So rotation of the matching is what you think it should be. And promotion is what I just explained. And now it doesn't matter whether you first apply the bijection and then rotation, or you first apply promotion and then the bijection. And from this, it's plausible that the order of promotion should be 2n, because there are 2 endpoints. And, yeah. Okay, now that's not new. But now we are making things more complicated. We introduce a third candidate. So now we have 3n people to cast votes and 3 candidates, Alice, Bob, and Charlie. And of course, Alice should win always. So Alice never trails Bob or Charlie. The relative position between Bob and Charlie is irrelevant here. So it may be that Bob is first or Charlie is first at some point, and then they switch and whatever. And here are the first voting configurations, and you see there are many. And again, there's a nice poset point of view. So these voting configurations are in bijection with the linear extensions of this poset. And somewhat surprisingly, Haiman Kreweras discovered a really, really beautiful formula for these. It's written here. This was in 65, so 1965, I should not say nowadays. So I wasn't even born then. Yeah, and it's beautiful. And one interesting thing about this formula is that there is not such a nice proof for it available. Well, it would be nice proof would be nice. Okay. Oops. And as you may have expected, there is promotion on these words also, and it works just the same way. You chop off the first letter, which must be an A, then you look for the first violation of our property, which is either a B or a C. You replace this B or C with an A and move it to the end. And then you get a Kreweras word again. And now the question is, what's the order of promotion on these words? And the very surprising answer is, it is nice. So the order is 6n. And moreover, if you apply promotion 3n times, so as many times as the word is long, then you just obtain the word where you switch all the B's and the C's. The A's stay in the same place, but all the B's become C's and all the C's become B's. And we also have a conjecture. So this is a theorem now. And we also have a conjecture about the character. And we have absolutely no clue how to prove this. Maybe brute force works, but we don't know and we didn't try. But it would be good. Okay, I invite you to do it. But what's really nice is we have a nice visual interpretation of this result. So we have a bijection between Kreweras words and something Schützenberger calls webs. And promotion intertwines with these graphs. And that's what I'm going to explain now. Before I do this, I just mention that promotion generalized to linear extensions of arbitrary posets, and up to, I don't know, 2021 or so, there were 4 infinite families of posets known, where the order of promotion is very nice, namely these 4 infinite families, and now we have 5, which is good. So how do we compute the order of promotion? And here a rather naive idea actually works. If we take this voting configuration and you remove all the Charlies, just one candidate drops out, then you get a dick word because Alice never trails Bob. And same thing happens if you remove all the Bobs. Okay, you get another dick word. And I told you there is a nice bijection between these dick words and non-crossing perfect matchings. Well, here you see it. And then the naive idea is to superimpose them, and we call it Kreweras bump diagram because that's a cool name. And now what we can do with this diagram is we associate a permutation with it. That's an idea which will come up again later. So I show you how it works. You see, maybe you see it's very light here. You see some crossings. There are some crossings here, and also there are some degenerate crossings here and here. So we call these crossings. And you start at some number, for example, at 3, and then you follow the arc. And whenever you encounter a crossing, you look up these 2 rules. And for example, you go from 3 to 2, you've just followed the arc, you encounter the crossing, and then you see, that's this rule, I should go back again. Okay, let's go back. So here's a crossing of 2 arcs. We are in this situation, and we come from here, so we should turn left, and so on. And when no rule applies, then we stop. And the permutation, and it's not completely obvious that it's a permutation, well, it's not hard either, is 3 is assigned the terminal city. There's a question? Above, yeah, here is a crossing, yes. So it's this rule. We go straight through. Okay. So the blue arc would be here. The rules are not clear. So this blue arc would be here. So this is the left. There is a left to right direction in this picture. But actually, I'm not going to explain it in detail because I want to explain other things, and this is relatively minor, but I can explain it to you in the coffee break. So essentially, there are local rules which tell you which way to turn, and then you get the permutation. And then it turns out the permutation is almost enough to determine this W, the Kreweras word, but not quite. You need a sign. Essentially, you need a sign for each connected component of this picture. So here we only have one connected component, but there might be several. You need a sign for this, and we encode it as another word. So this whole word is one bit of information in truth. Namely, you can say whatever letter you choose here, it's B or C. And then these two words determine the permutation, and the sign, these two determine the Kreweras. This is important. And now it turns out that using a very simple geometric argument, you can, which I will not explain in detail now, you see that the permutation for the promoted word is the permutation for the original word rotated. And rotation means conjugation with the long cycle, or draw the permutation in a cycle and turn it. And also the epsilon is obtained, the epsilon of the promoted word is obtained in a very easy way from the epsilon of the original word. And from this lemma, it's immediate that the order of promotion is 3n. Everything before is details. But now comes something extremely mysterious, and I really want to explain this. So this is Greg Kuperberg, and he invented webs. So webs as in for spiders. And for our purposes, an SL3 web is a planar graph W, just as you saw before, embedded in a disk with 3n wide boundary vertices arranged counterclockwise, and such that W is trivalent, which means the internal vertices all have degree 3, and the vertices on the boundary all have degree 1. Or if you want to connect them, they also have degree 3, but then as you like it. Second condition is W is bipartite, so a black vertex has only white neighbors, and vice versa. And the third condition is W is irreducible. That's a strange condition. it means that there are no internal faces with fewer than 6 sides. So 6 sides is okay, 7 is okay, and so on, but 6 sides, 5 sides is not okay, and 4 sides is not okay. And it turns out that, well, that's the reason why they were invented. SL3 webs are in bijection with 3 times n rectangular standard Young tableau. And now something very mysterious happens. Oops. There is a bijection between Kreweras words and something we call Kreweras webs, which are SL3 webs without internal faces having a multiple of 4 sides. So we have this really weird extra condition. And also each connected component is assigned one of the 2 colors, blue or crimson. That corresponds to the epsilon we had before. Warning, irreducible has nothing to do with components. Okay, irreducible means something about the minimal size of an internal face. The question is, does it mean the faces have at least 6 sides? Yes. Yeah. So 6 sides is okay, 8 sides is not good, 10 sides is okay, 12 is not good, and so on. And this bijection intertwines promotion and rotation, which was in the picture at the very beginning. And how does it work? I show how it works to make you believe that it's mysterious. So it works in a completely naive way. You take this bump diagram we had before, that's the only reason why I introduced the bump diagram, and you break up crossings. So I said already, the bump diagram has a direction. So the arcs go from left to right. And so this is actually well defined. You can make this precise. Here I introduce this extra avocado edges. And so here I do it. For each crossing, I introduce an extra avocado edge. And then I write down the numbers from 1 to 9 on the circle, and I make everything straight. And then I forget the colors. One thing we actually can understand is that this picture will not have faces with 4, 8, 12, 16 sides. Why is this? We start with something like this. So this is a part of a Kreweras bump diagram. And since it is, since the color of the edges alternate, this must have 2k sides. That's obvious. And now we introduce these avocado edges. So we get 4k minus 2 sides. Okay. Interestingly, the converse is very non-trivial. So it's strange that this works. So it's obvious that you only get a web which does not have a multiple of, it's obvious that you don't get webs where internal faces have 4 or 8 or 12 sides, but that this is actually also sufficient is completely mysterious to me. I did not yet explain why this works in total. Well, we pull out another math magician, and we invent, well, actually this is Alex Postnikov, invented some rules of the road. If you see a black light, go right. And if you see a white light, go left. Okay, so these are a bit easier. And if you start, where did you start? If you start from 3, I follow the road. I see a black light, I turn right. I see a white light, I turn left. Black, white, black, and update. And you get this permutation. And we can prove by following the rules that the trip permutation of the Kreweras bump diagram is actually the same as the trip permutation of this Kreweras web. And it was funny for us because we discovered it exactly in this sequence I told you. So we found this Kreweras bump diagram and we're happy. Oh, we can show promotion as order 3 as 6n. And then we discovered these webs and we were even happier because it's the same as this very old trip permutation from 2006. And then we were even happier, meta happy, because Postnikov proved that the trip permutation determines, oops, there's a mistake, determines the playback graph. So it determines this graph. There's a mistake here, the uncolored graph. And now we do it for every component and assign the color and we get the Kreweras web. So as a corollary, we find that promotion of a Kreweras word is the same as the rotation of the Kreweras web. And with this mystery, which I still don't understand, I would like to stop.
Thank you for that more visual art. Any questions? Yes, or lots of.
So you have these mysterious conditions that you have right on the previous page here, right? So have you tried removing some of these and checked in the OS what they enumerate and see if you have?
We can actually enumerate them. So the question is, what happens if we remove some of these conditions? Well, for one thing, if the main condition is actually this with the 4 sides. If you remove this condition, you get SL3 reps, and these are just 3 times n standard Young tableau. Okay, and if you don't remove it, we can count them. Yeah.
And if you add
even so, we get a refined counting. We can refine with the number of components. Does this answer your question? Not quite.
Well, then you can add conditions, and I mean, you can not have a multiple of say 8 or not have a multiple of 3.
Okay, no, we don't get anything interesting. Well, we don't get anything we understand better then. Yes, thank you. So, yeah.
The Young tableau of rectangular height things, webs, etc. You didn't mention this.
Yes, that's the mystery. We don't understand it. Yeah, okay. How is this related? Excuse me. How is this related to the work of Peterson, Pilavsky, and Rhodes, where they have promotion for webs? So they use Kuperberg's webs to show essentially. So that's the. I think that's. I'm not sure whether this is the main theorem. They compute the character for 3 times n standard Young tableau. And I should also mention there is a big open question: what are webs for SL4 or SL5? There's no nice basis known for them. There are webs, but no basis set. So the question was, how is this related to the work of Peterson, Pilavsky, and Rhodes? And the answer is, we don't know. The webs just pop up for no good reason. And I would love to see some algebraic reason why they appear here, but we have no idea. And even we stumbled over them. So it was complete coincidence that we discovered this.
Could it be related? Well, I'm thinking of these words as being highest weight elements when you restrict to SL2 in 2 different ways. One, the natural way, and one with the epsilon1 minus epsilon3 roots. Can you see it from that perspective?
Not yet, but I'd like to talk with you about this. This would be brilliant.
I'm not sure if you have already addressed this during the talk, But if we replace 3 cross n with some other fixed shape, is there some version of the theorem that we get?
Excuse me, I did not understand the question.
So instead of considering 3 cross n standard tableau, if I fix some other shape and look at standard tableau of that shape, is there a version of webs that I get? Is there a version of Kreweras words that I get?
Not that I know of. And I think it actually, there was some work, but I forgot where. I might recall, but not in a very natural way. So free time rectangular standard Young tableau correspond to the invariant tensors. They are highest weight words. And if you don't have rectangular shape, you lose this highest weight property. So that's the reason why rectangular appears. It should exist for 4 times n or 5 times n, but nothing is known here.
Yeah, so I've got 2 questions this time. Right. So my first question is, you have these arc diagrams for non-crossing set partitions. So you have these arcs for non-crossing set partitions, but then you also have set partitions where you have crossings, right? And then so is there an analog for Kreweras set partitions where you have arcs of 2 different colors? And that is an interesting object to look at.
So the idea, so the question is, can we generalize to set partitions?
Yes.
Okay. It seems that it's not possible, or it's not completely obvious. So I mean, I could try, but it was, so one, especially Sam Hopkins, tried very hard to find posets with nice order of promotion. And as you see, up to 2021, only 4 families were known, and there was a lot of promotion advertisements to look for further families. And well, now we have one.
So if I can have one more question. Yeah, so you have a formula with a Q counting, right?
Yes.
I was just wondering if there's some statistic that comes up there. And can you plug in more variables?
Just a moment. I'm looking for the, you mean the Q analog?
Yes.
Here. This is a conjecture. We cannot prove this.
But for the version that's known, the original version.
This?
Yes.
Oops, it's a major index. Or a major index, some major index. Yeah. No, I don't think we don't have a statistic yet. But to be honest, I did not look very hard into this. I checked the formula for numerically to reasonable size. So I'm absolutely sure that it's correct. But no, not absolutely. I'm quite sure that it's correct. Yeah. You see the pictures get very large because of this condition, no multiple.
Okay, let's thank Martin once again.